in this video, I wanted to talk about proving a trigonometric identity and how do we even get started? How do we do that? Like looking at a few examples from our packet, let's say we wanted to prove this trigonometric identity. Basically, we're going to look at a lot more complex equations, and always the implication for questions like this is an identity. This must be true. And like the idea and the goal is to take prior identities that we know and use these facts to show something new is true. But often that's a lot harder, and that's kind of what I get into is what strategy can we apply to solving this. And if you look in your packet, there's kind of a set of guidelines, and that's what I wanted to start with. Is what are some guidelines to help me get going in a proof? But number one, it suggests to start with one side of the identity. Basically, pick one side of the equation, write it down. Your goal is to transform it into the other side. It is usually easier to start with the more complicated side. So this is actually a very important note, something that I've found to be universally pretty much always true. That we want to start with the more complicated side. Now, this might seem counterintuitive because usually something that's easier, we like to deal with that, like, right? Because if it's easier, it's better. But in a trigonometric identity, which is just an equation that must be true for all values rather than some values. Remember, that's the only meaning of identity besides an equation. So if we're looking at this hypothetical identity, notice that also just something I wanted to mention. If an example asks you to prove something, the implication is this is true. Now, we don't necessarily understand why it's true. That's kind of our goal, is to figure out why. But it's not like, well, maybe it is, maybe it isn't. Like that's like that would be a trick question. Sometimes a question could ask you, is this an identity? That's actually way harder. If it just tells you to prove it's an identity, then we already know it must be true, and our goal is to somehow prove that. But basically, in this case, what it would step one said to do is pick one side, write it down. Generally, it's easier to start with the harder side. So let's go ahead and do that. But like in this case, we have, I would say that the more complicated side is the left-hand side of that equation, which is cosine theta times secant theta minus cosine of theta. And the reason why it's usually easier to start with the more complicated side is because we can take this combination of multiple trigonometric expressions and try to simplify it. Just like we were doing in the last video, it's actually a lot easier to take something complicated and make it simpler than to take something simple and try to turn it into this. Because really the goal is to start with one side and somehow through a series of algebraic manipulations using true identities, somehow morph it into sine squared. And at the very beginning, it might seem impossible. How is any of this going to make sine squared? But as we saw in a lot of the prior examples, quite complicated things can turn into quite simple things if we know what to do. And that's kind of the idea, is we're going to be using a lot of these rules in order to do that as well. And also, there's a warning on your packet which says do not perform operations on both sides of the identity you're trying to prove. And the reason why is that if you, like, say for example, I was to add 2 to both sides, or rules of equations which are true, now those rules are still true and still fine, but in proving an identity, sometimes using certain operations on both sides can cause issues. And usually it's just easier to follow the train of logic where I'm not working with both sides, because that tends to muddy the issue a little bit. I'm just going to start with one side and then through a series of steps using verified identities, change that into the other side somehow. But anyways, I'm not going to be, it's very different strategically than solving an equation. It's nothing like it really. I'm kind of taking one side, simplifying, and trying to make it into the other side. And logically, if I can do that, I will have proved that it is true. But basically, one of the things I would start with is kind of like with simplifying identity or simplifying expressions, trying to change everything to terms of sine and cosine. Like in this example, sorry, my tablet. Oh no, it's my pen that's not working. All of a sudden, I don't know why. Maybe it's dead. Sorry, give me just 1 second to see if my pen will be fixed. Okay, there it goes. That is odd. My Apple Pen decided just to not work for a minute. Okay, I think we're set. So if we change secant, well, secant is the reciprocal of cosine, so secant is 1 over cosine. And these are just things you would need to remember if you were to be able to prove identities. So to be able to prove identities, you have to have a pretty good grasp on those fundamental identities, which is why I'd practice using them. And in your homework, you're going to have a handful of identities to practice trying to prove. And most likely you'll struggle on some of them. That's very, very common. And so in these next couple of videos, I wanted to show you some of the tricks and some tips in terms of how to deal with more complex identities and get some extra algebraic strategy for addressing those. Though this one's pretty easy. Also, something that I'm not going to make you do on a test, but one thing that you could do is as you're working on an identity, what you could do is like justify your series of actions by telling what identity you use. Like in this case, this was reciprocal identity. And so that way, if someone was trying to trace back my work, they could kind of figure out, okay, what did I do from the first step to this step? And, I could kind of say what it is that I'm doing in this particular step. But I'm going to go ahead and do that in this case. Usually we don't do this because hopefully it's obvious as to what I'm doing. But to those who are not familiar or are new with identities, it's a good thing to do. So that way I know, okay, what did I do? I could go look it up later or Google it or whatever to see what it is. But what I could do next is, well, notice that I have a situation where I have something times something minus something. And I could apply the distributive property here if I wanted to. And the reason I would do this is notice that if I distribute cosine into 1 over cosine, that would make cosine over cosine. And then if I distribute cosine into cosine, cosine times cosine is going to be cosine squared. And well, of course, cosine divided by cosine, anything divided by itself is equal to 1. And it greatly simplifies. But from here, I could say, well, what did I do? I used the distributive property, right? Because that's exactly what happens. That's not really a trigonometric identity. That's just a basic algebraic identity. And then I used cancellation, right? I mean, do I even have, like, another thing is, do I have to justify all these? In this case, probably not. These are just obvious properties, but, it's all depending on who's reading it, who's, a lesser or a student in a lower level of math might not think of each one of these steps as obvious. But anyways, another thing is sometimes we might get stuck at a point where, okay, now I have 1 minus cosine squared. How do I finish this? And another thing that I recommend is always keep in mind, well, what's the goal? My goal is to start with the more complicated side and somehow simplify it enough to make it look like the other side. And also knowing what I'm trying to get can help you figure out where we're going, because my goal is to get to sine squared, but what I'm left with is 1 minus cosine squared. And in these situations, again, it might not be obvious, but the Pythagorean identities are the ones that can greatly help with squares, because those Pythagorean identities, the ones like sine squared plus cosine squared equal to 1, help relate, well, how do sine and cosine relate in squares? But another property that is important to mention is we can use these identities in alternate forms. You don't have to necessarily do exactly, it doesn't have to look exactly the same. And I'm not being very clear about what I mean here. But let me just move over to the side and scratch down a little note. Well, sine squared plus cosine squared of theta must be 1 always, regardless. It doesn't have to be theta. It could be any variable. But I could use both sides, because this is ubiquitously true for any theta. But let's say, for example, I wanted to subtract cosine squared to either side. Well, this is an equation, and I can use valid properties of equation, right? I could subtract the same thing from both sides, and it should still remain equal. That's just, another basic property of algebra. But what this does is it provides me with an alternative version to the original Pythagorean identity. So this was like the original one on the sheet with all those basic fundamental identities. But another obvious result is, well, since sine squared plus cosine squared is 1, 1 minus either of them squared gives you the other. 1 minus cosine squared is sine squared, and 1 minus sine squared is cosine squared. But all that being said, notice what I have here is 1 minus cosine squared, but that must be equal to sine squared by the Pythagorean identity. So the final step here is actually just to finish the question, sine squared theta, and that's by the alternative Pythagorean identity. And that concludes my proof. And a lot of times when people write proofs, they will put a little box or a little various other symbols, which often stand for QED, which just kind of means I'm done, I've finished what I've done. And it's kind of a way to indicate to the reader of your proof, how do I know when I'm done? But I'm in a habit of doing that after with trigonometric identities, but it's something you don't need to do necessarily. And some people use an open box or whatever. It's kind of an archaic symbol, well, in my opinion. But anyways, it's useful, and sometimes proofs are not quite this short, and you might not think of this as short, but a lot of times in advanced mathematics, proofs could take pages or 5 pages of work just to get through it. So if you were trying to look for, well, where is the end? It's kind of helpful as a way of symbolically pointing out, okay, this is now done. Anyways, also, so what is the point of what I've done? What I've done is I've taken the left-hand side, I've shown through a series of irrefutable steps that it must be equal to sine squared, and I have hence proved that this is equal to this. And that is the essence of proving a trigonometric identity. Starting with one side, showing through a series of previously derived steps that I can wind up with the other side. And also, in so doing, when I prove a new identity, this actually, it kind of expands my toolbox. Because initially, we have all these fundamental identities, but as we start proving new identities, we learn new ways that the trigonometric functions are related. Well, now I know that sine squared is equal to all this other crap. Well, what did I really know? Is this really going to be very helpful? Probably not, but these are just kind of exercises to practice the idea. But as we learn in the next couple sections of the book, we're going to discuss more and more types of identities. And we're going to talk about, well, why are these alternate identities, why are these useful? Because a lot of alternate identities are really quite useful. And at the end of the day, I think the moral of the story here is that, well, trigonometric functions can all look alike. They all you can convert one into another, and a lot of the time they relate to one another in ways that we might not necessarily originally expect. In the next video, we'll do another couple examples of proving identities. We'll expand to slightly harder ones, and then I'll leave some for you to practice on your own in addition to the homework.